Welcome to the Sleepy Scholar, your sanctuary of serenity where knowledge whispers and consciousness fades. In each episode, we embark on a cerebral voyage into the heart of humdrum, exploring topics so meticulous and profound that they beckon the mind to quieten and the eyes to grow heavy. With every word, we weave threads of thought into a tapestry of tranquility, guiding you gently towards the cusp of slumber. Here, complexity meets calm, and enlightenment is lulled by the lullaby of learning. So, adjust your pillows, let the dim glow of your device be the last light you see, and prepare to drift into dreams on the soft wings of scholarly discourse. This is the Sleepy Scholar, where dullness is a delight, and sleep the sweetest fruit of tedium. Let the journey begin.
A black hole is a region in space where the gravitational pull is so strong that nothing, not even particles and electromagnetic radiation such as light, can escape from it. The theory of general relativity predicts that a sufficiently compact mass can deform spacetime to form a black hole. The boundary of a black hole, beyond which no escape is possible, is called the event horizon. Although the event horizon has an enormous effect on the fate and circumstances of an object crossing it, no detectable features are observed. In many ways, a black hole acts like an ideal black body, as it reflects no light. Moreover, quantum field theory in curved spacetime predicts that event horizons emit Hawking radiation with the same spectrum as a black body of a temperature inversely proportional to its mass. This temperature is on the order of billionths of a Kelvin for black holes of stellar mass, making it essentially impossible to observe. Black holes of stellar mass are expected to form when very massive stars collapse at the end of their life cycle. After a black hole has formed, it can continue to grow by absorbing mass from its surroundings. By absorbing other stars and merging with other black holes, supermassive black holes of millions of solar masses may form. There is general consensus that supermassive black holes exist in the centers of most galaxies. The presence of black holes has been inferred through various astronomical observations, particularly when studying the motion of stars and gases in the vicinity of the center of galaxies. In some cases, such as in the center of the Milky Way, observations have identified stars that orbit around a particular region in space, suggesting the existence of a supermassive black hole. More direct evidence of a black hole comes from studies of the radiation emitted by gas and dust that is accelerating and heating up as it falls into a black hole, known as accretion. The detailed study of this accretion process is an active area of research in astrophysics. Historical background and discovery. The historical background of black holes begins long before they were ever proven to exist. The idea of a body so massive that not even light could escape from it was first put forward by John Michell in 1783. He used Newton's theory of gravity to hypothesize the existence of dark stars. Later, in the 20th century, Carl Schwarzschild found a solution to Albert Einstein's field equations, which described the gravitational field around a spherical mass, leading to the concept of the Schwarzschild radius. This radius represents the size of the event horizon of a non-rotating black hole. Einstein's general theory of relativity, published in 1915, predicted the existence of black holes. However, Einstein himself was skeptical that they would actually be a physical reality, regarding them as a mere mathematical curiosity. It wasn't until the 1960s, with the advent of more sophisticated telescopes and detection methods, that the first physical evidence for black holes was discovered. Astronomers identified objects that were too compact, massive, and dark to be anything other than black holes. These objects were located in binary systems, where the visible star orbited an unseen companion, or in the centers of galaxies where immense gravitational forces indicated the presence of a supermassive object. The term black hole was coined in 1967 by American astronomer John Archibald Wheeler, and it quickly became popular in the scientific community. The discovery of pulsars supported the existence of stellar mass black holes, and the first strong candidate for a black hole, Cygnus X1, was discovered in 1971. This object was found to be emitting powerful X-rays, which could only be explained by the presence of a black hole accreting matter from a companion star. The study of black holes moved from theoretical to observational with the use of X-ray astronomy, which could detect the high-energy phenomena associated with black holes. More recently, the LIGO and Virgo gravitational wave observatories have opened a new window into the study of black holes by detecting the waves produced when black holes merge. In 2019, the Event Horizon Telescope project captured the first image of a black hole's event horizon, providing direct visual evidence of their existence. This black hole, located in the galaxy M87, offered a look at the shadow of the event horizon, surrounded by a bright accretion disk. As the study of black holes progresses, they continue to challenge our understanding of physics, particularly at the intersection of quantum mechanics and general relativity, and remain one of the most fascinating subjects in modern astronomy and theoretical physics. Theoretical foundations, general relativity, and Schwarzschild radius. The formation of black holes is a process typically associated with the gravitational collapse of heavy objects such as stars. It occurs when a star has exhausted the nuclear fuel in its core, resulting in the core collapsing under the influence of its own gravity. This process can lead to different outcomes depending on the initial mass of the star. For a star with a mass below about 3 solar masses, the collapse will be halted by electron or neutron degeneracy pressure, leading to the formation of a white dwarf or a neutron star. However, if the core's mass exceeds the Tolman-Oppenheimer-Volkoff limit, thought to be around 2 to 3 solar masses, no known form of degeneracy pressure can prevent further collapse, and a black hole will likely form. The collapse causes the density to increase to such high levels that the escape velocity at the surface exceeds the speed of light. This surface, the event horizon, is not a physical boundary, but an imaginary one from which nothing can return once crossed. In addition to the stellar mass black holes formed by the collapse of massive stars, there are supermassive black holes, which are millions to billions of times more massive than our Sun, and are found at the centers of most galaxies, including our Milky Way. The origin of these supermassive black holes remains an active area of research, with theories suggesting they may form through the collapse of massive gas clouds in the early universe, the merger of smaller black holes, or from a large star cluster collapsing under its own gravity. Intermediate black holes, which range between stellar and supermassive black holes, are another category that has been proposed to fill the gap between these two well-known classes. There is evidence for their existence, such as the observation of ultraluminous X-ray sources in other galaxies, but it is not as robust as for the other types of black holes. Lastly, primordial black holes are a hypothetical type of black hole that could have formed immediately after the Big Bang, from density fluctuations in the very early universe. These would not have formed by stellar collapse, but rather through the direct collapse of extremely dense regions. While there is no direct evidence of their existence, they remain a topic of interest for their potential role in dark matter and other cosmological phenomena. Formation of black holes. Stellar evolution leading to black holes. Stellar evolution is the process by which a star changes over the course of time. Depending on the mass of the star, this life cycle can end in the formation of a black hole. Stars sustain themselves by nuclear fusion, converting hydrogen into helium and releasing immense amounts of energy in the process. As stars run out of hydrogen in their cores, they begin to fuse helium and heavier elements. But this can only continue until iron is produced, as fusing iron does not release energy. For stars much more massive than the Sun, once nuclear fusion in the core ceases, the core becomes unstable and contracts under its own gravity. This contraction heats the core up, causing the outer layers of the star to expand, and the star becomes a red supergiant. If the core mass is sufficient, the end result of this contraction is a supernova explosion, where the outer parts of the star are expelled into space. The supernova explosion is a critical moment in the formation of a black hole. If the remaining core mass after the explosion is greater than about 3 solar masses, it will continue to collapse to form a black hole. The core shrinks to a point of infinite density, a singularity, where the curvature of space-time becomes infinite. During this collapse, a point is reached where the escape velocity exceeds the speed of light. This defines the event horizon of the black hole, the boundary beyond which nothing can escape. The size of the event horizon is proportional to the mass of the black hole and is described by the Schwarzschild radius formula. The process by which stars evolve and potentially become black holes is influenced by a variety of factors, including initial mass, composition, and the presence of binary companions. In binary systems, matter can be transferred from one star to another, which can alter the evolutionary path and the manner in which a black hole might form. Furthermore, the rotation of the star can also influence the nature of the collapse and the properties of the resulting black hole. Stellar evolution leading to black holes is a field rich in research, as it bridges the gap between the life cycles of stars and the dynamic phenomena associated with black holes. Observations from telescopes and space missions, along with theoretical modeling, continue to enhance our understanding of this fascinating and extreme endpoint of stellar evolution, supernova and the creation of stellar black holes. When a massive star has burned through its nuclear fuel, it undergoes a catastrophic collapse leading to a supernova, an explosion that outshines entire galaxies for a brief time. This event is a critical stage in the creation of stellar black holes. The core of a dying massive star, depleted of its nuclear fuel, succumbs to gravitational forces and collapses. As the core contracts, the protons and electrons in its atoms are squeezed together with such force that they combine to form neutrons and neutrinos. The core becomes a tightly packed ball of neutrons, known as a neutron star. However, if the mass of the core is too great, more than about 3 times the mass of the Sun, not even neutron degeneracy pressure can halt the collapse. The core's collapse halts abruptly as it reaches an extremely high density, causing the infalling material to bounce outward, creating a shock wave that propagates through the outer layers of the star. This shock wave, along with a huge number of neutrinos rushing outward from the newly formed neutron star, blows the outer layers of the star apart in a supernova explosion. If the core left over from a supernova explosion is sufficiently massive, the collapse continues unabated and a black hole is formed. This black hole has an escape velocity greater than the speed of light at its event horizon, making it invisible against the backdrop of space. The freshly formed black hole may continue to accrete material from the surrounding stellar remnants, growing in mass and potentially emitting X-rays as matter is heated during the accretion process. This is how many stellar black holes are detected in the universe. The creation of a stellar black hole from a supernova is a rare event, as it requires a progenitor star of at least 20 solar masses. The exact number of stars that end their lives in this way is uncertain, and is a topic of ongoing astronomical research. The study of supernova and their remnants provides critical insights into the life cycles of stars, the enrichment of the interstellar medium with heavier elements, and the conditions under which black holes form. Observations of supernova and their aftermath are key to understanding not only the nature of black holes, but also the evolution of galaxies and the universe itself. Other types of black holes: intermediate, supermassive. In addition to stellar black holes, the cosmos harbors other types, notably intermediate and supermassive black holes, each playing a unique role in the cosmic landscape. Intermediate black holes are an elusive class with masses ranging from 100 to several 100,000 solar masses. They bridge the gap between stellar black holes and the supermassive giants lurking in galactic centers. The existence of intermediate black holes is inferred from indirect evidence, such as the observation of ultra-luminous X-ray sources in external galaxies, which are too bright to be stellar black holes, but too small to be supermassive black holes. The formation mechanisms for these black holes are not well understood, but they may form through the merger of stars in dense stellar clusters, the collapse of massive clouds of gas, or the accretion of matter onto smaller black holes. Supermassive black holes, millions to billions of times the mass of the Sun, are generally found at the centers of galaxies, including our own Milky Way. They influence the dynamics of their host galaxies and are thought to play a crucial role in galaxy formation and evolution. The prevailing theory is that they grow from smaller seeds, either from the remnants of early stars or direct collapse of primordial gas clouds in the early universe, and then increase their mass by accreting stars and gas from their surroundings and by merging with other black holes during galaxy collisions. The strong gravitational pull of supermassive black holes affects the orbits of stars in the galactic center and can result in the emission of powerful jets and radiation, particularly when matter is actively accreting onto the black hole. This accretion process can power active galactic nuclei and quasars, some of the most luminous objects in the universe. The study of these different black holes is not only crucial for understanding the properties of the black holes themselves, but also for shedding light on the more extensive processes that govern the formation and growth of structure in the universe. Observations across the electromagnetic spectrum, along with gravitational wave astronomy, are providing new insights into the life cycles of black holes and their interaction with the cosmos. Properties of black holes: event horizon and singularity. The event horizon and singularity are two fundamental but drastically different components of a black hole. The event horizon is the boundary that defines the region of space around a singularity from which nothing can escape the gravitational pull of the black hole, not even light, hence the name black hole. It's the point of no return. Once crossed, the inexorable pull of the black hole's gravity will draw matter inward. The size of the event horizon is directly proportional to the mass of the black hole and is described by the Schwarzschild radius for non-rotating black holes. For rotating black holes, described by the Kerr solution of Einstein's equations, the event horizon is more complex due to frame dragging effects. The singularity is an area of intense research and speculation. Since our current theories of physics are not capable of describing such a regime, the true nature of singularities is still a mystery. It is widely believed that a theory of quantum gravity would be needed to fully understand the core of black holes, potentially smoothing out the singularity to some finite density. The concept of the event horizon has been challenged by theories like the firewall hypothesis, which suggests that the event horizon could be a region of intense radiation, defying the notion that crossing the event horizon is an uneventful process. Another theoretical feature related to the event horizon is the ergosphere, which is a region outside of the event horizon where objects cannot remain in place due to the dragging of spacetime. The properties of the event horizon and the singularity are key to the many peculiar and intriguing effects associated with black holes, such as the intense tidal forces near the event horizon or the potential for time dilation effects predicted by relativity. Understanding these properties is crucial for explaining how black holes interact with their surroundings, including how they accrete matter and influence the space around them. Hawking radiation theory. Hawking radiation is a theoretical prediction that suggests black holes are not completely black, but emit small amounts of thermal radiation due to quantum effects near the event horizon. This concept was proposed by physicist Stephen Hawking in 1974 and has been a significant topic in theoretical physics. The theory combines principles from quantum mechanics and general relativity. According to quantum field theory, pairs of virtual particles and antiparticles spontaneously form and annihilate each other constantly in empty space. Near the event horizon of a black hole, these pairs can be separated by the extreme gravitational field. If one particle falls into the black hole while the other escapes, the escaping particle becomes real, and takes energy away from the black hole. This radiation implies that black holes can lose mass and energy over time, as the energy for the radiation comes from the black hole's mass, leading to a gradual decrease in size. Ultimately, Hawking's theory suggests that black holes could evaporate entirely through this process over astronomical timescales. Hawking radiation has never been observed directly, as the amount of radiation predicted for stellar black holes is minuscule and overwhelmed by other sources of radiation in the universe. However, for microscopic, primordial black holes, this radiation would be significant, and its detection would provide strong evidence for their existence. The concept of Hawking radiation also leads to the black hole information paradox, one of the biggest unsolved problems in theoretical physics. This paradox arises because the radiation seems to carry away information about the matter that fell into the black hole, leading to a potential conflict with the law of quantum mechanics that information cannot be destroyed. Hawking radiation represents one of the most fascinating aspects of black holes, bridging the gap between quantum mechanics and gravity, and continues to fuel research and debate in the quest for a more profound understanding of the universe. Mass, charge, and spin, the no-hair theorem. The no-hair theorem is a conjecture in astrophysics that asserts black holes, when fully settled into their final state, can be completely described by just three externally observable classical parameters: mass, electric charge, and angular momentum or spin. The theorem gets its name from the saying that black holes have no hair, where hair metaphorically denotes additional features or complexities. Mass is the most fundamental property of a black hole and dictates the strength of its gravitational attraction. It determines the size of the event horizon and can be inferred from the orbital characteristics of material, such as stars or gas around the black hole. Charge is the electric charge of a black hole. In theory, a black hole can have a net electric charge if it captures charged matter. However, in a realistic astrophysical environment, black holes are expected to be nearly or completely neutral. This is because the presence of a significant charge would attract oppositely charged particles from the surrounding plasma, which would quickly neutralize the black hole. Spin refers to the angular momentum of a black hole, which is a measure of its rotation. Black holes can spin at near the speed of light. The spin affects the space around the black hole in a way that non-spinning black holes do not. It drags space-time around with it, a phenomenon known as frame dragging. The spin of a black hole is associated with a number of observable effects, including the potential to power relativistic jets of particles that can be projected for vast distances. The no-hair theorem implies that all other information about the matter that formed a black hole or is falling into it disappears behind the event horizon and is therefore unobservable from the outside, contributing to the black hole information paradox. This is contrary to the expectations from quantum mechanics, in which information is conserved, and has led to a vigorous debate about the ultimate fate of information in a black hole, involving concepts such as Hawking radiation and firewalls. The simplicity implied by the no-hair theorem makes black holes unique among astrophysical objects. If the theorem holds true, then all complex information about the collapsing star and any other material absorbed by the black hole, including density, shape, etc., is irretrievably lost from the universe when it crosses the event horizon, leaving behind only mass, charge, and spin to mark its existence. Types of black holes. Stellar black holes. Stellar black holes are formed by the gravitational collapse of massive stars during a supernova explosion. These black holes have masses ranging from about 5 to several tens of solar masses. They are characterized by their dense core remnants after the outer layers have been expelled. The process begins when a star with a mass greater than about 20 times the mass of the Sun exhausts its nuclear fuel. Without the outward pressure generated by fusion, the core is unable to counteract the gravitational forces trying to compress it. As a result, the core collapses, and if the remaining mass is sufficient, it overcomes all known repulsive forces that could halt the collapse, leading to the creation of a black hole. These stellar remnants are scattered throughout galaxies, often residing within the same regions where star formation occurs. When they are in binary systems, stellar black holes can accrete matter from their companion stars. This accretion process can lead to the emission of X-rays and other forms of radiation, making the black holes detectable by X-ray telescopes. One of the most famous stellar black holes is Cygnus X1, which was the first object to be widely accepted as a black hole by the astronomical community. It was discovered due to its strong X-ray emissions, which arise from the accretion of material from a companion star. Stellar black holes are also of interest because they can merge with other black holes or neutron stars, producing gravitational waves that can be detected by observatories on Earth, such as LIGO and Virgo. These observations give scientists unique insights into the properties of black holes and the nature of gravity. Understanding stellar black holes is not only critical for the study of the life and death of stars, but also for exploring the fundamental laws of physics under the most extreme conditions. Supermassive black holes. Supermassive black holes are colossal objects located at the centers of galaxies, including our own Milky Way. They range from millions to billions of times the mass of the Sun. Unlike their stellar mass counterparts, which form from the gravitational collapse of massive stars, the origin of supermassive black holes is not fully understood. The leading theories suggest they could have formed from the direct collapse of massive gas clouds in the early universe, the runaway collisions of stars in dense star clusters, or the growth of smaller black holes that accrete matter and merge over time. The supermassive black hole at the center of the Milky Way is named Sagittarius SGRA. It has a mass approximately 4 million times that of the Sun, and it influences the orbits of stars in its vicinity. The motions of these stars provided some of the first evidence for the existence of supermassive black holes. Supermassive black holes play a crucial role in the evolution of galaxies. They can drive powerful jets that extend far beyond their host galaxies, and they are believed to regulate star formation by heating intergalactic gas and by ejecting material in energetic outflows known as feedback processes. These processes can influence the growth of the host galaxies, leading to the observed correlation between the masses of supermassive black holes and the properties of the galactic bulges that surround them. The accretion of gas and dust onto supermassive black holes is also responsible for some of the most luminous phenomena in the universe, such as quasars and active galactic nuclei. These objects can outshine the combined light of all the stars in their host galaxies and can be seen across the observable universe, providing valuable beacons for studying the distant cosmos. Observations of supermassive black holes, particularly of the regions close to their event horizons, are challenging due to their vast distances and the small angular size of their event horizons. However, the Event Horizon Telescope, a global network of radio telescopes, has successfully imaged the shadow of the event horizon of the supermassive black hole in the galaxy M87, providing direct visual evidence of this phenomenon and marking a significant milestone in black hole astronomy. Supermassive black holes continue to fascinate scientists and the public alike, offering a window into the processes that shape the universe on the grandest scales. Intermediate and primordial black holes. Intermediate black holes are a class of black holes that bridge the mass gap between stellar black holes and supermassive black holes. They have masses ranging from 100 to several 100,000 solar masses. The existence of intermediate black holes is supported by indirect evidence, such as the observation of ultra-luminous X-ray sources in external galaxies, which exceed the luminosity expected from stellar black holes, but are less luminous than typical active galactic nuclei powered by supermassive black holes. The formation of intermediate black holes is still a subject of research. Some theories suggest they could form from the merger of stellar mass black holes or through the runaway collision and amalgamation of stars in dense stellar clusters. Another possibility is that they could be remnants of very massive stars that existed in the early universe, which avoided complete disruption during their supernova explosions. Primordial black holes, on the other hand, are hypothetical black holes that could have formed in the very early universe, long before stars began to shine. If they exist, they would be relics from the Big Bang and are posited to have formed due to fluctuations in the density of the universe shortly after the Big Bang. These fluctuations could have created regions dense enough to collapse under their own gravity, forming black holes directly from intense pressure without the need for a star to collapse. Primordial black holes could theoretically have any mass, from very small to many thousands of times the mass of the Sun. They are unique among black holes in that their masses could be lower than the stellar mass black holes that form from the gravitational collapse of stars. If light enough, primordial black holes could evaporate over cosmological timescales through Hawking radiation. The detection of primordial black holes would provide invaluable insights into the conditions of the early universe and could potentially identify a candidate for dark matter. However, despite extensive searches, there is yet no direct observational evidence for their existence. If they are found, they could vastly increase our understanding of the universe's infancy and the nature of dark matter. Observation and evidence. Indirect observations, accretion disks, gravitational lensing. Indirect observations of black holes are necessary because black holes themselves emit no light. However, they can be detected through their interactions with the environment. Two key phenomena used for such detections are accretion disks and gravitational lensing. Accretion disks. An accretion disk forms when material, such as gas from a nearby star or interstellar medium, falls towards a black hole. The conservation of angular momentum causes this material to spiral inwards, forming a rotating disk. As the material in the disk spirals closer to the black hole, it accelerates and heats up due to friction and compressive forces, reaching extremely high temperatures and emitting large amounts of electromagnetic radiation, especially X-rays and gamma rays. This radiation can be observed by space-based telescopes and is one of the most reliable indicators of the presence of a black hole. Additionally, the study of the spectral lines of the radiation can provide information about the velocity and composition of the accreting material, offering insights into the properties of the black hole and its accretion disk. Gravitational lensing. Gravitational lensing occurs when the intense gravity of a black hole bends the path of light from a background object, much like a lens. This effect was one of the first predictions of Einstein's general theory of relativity. There are several types of lensing, such as strong lensing, where multiple images of a single astronomical object are visible, and weak lensing, where the background object appears distorted but not multiply imaged. Microlensing is another form, where a black hole passes in front of a distant star, and the gravity of the black hole acts as a lens to magnify and brighten the distant star's light temporarily. Gravitational lensing does not only confirm the presence of a black hole, but can also be used to estimate its mass, and provides a unique tool for probing both the black hole and the structure and distribution of matter in the universe. Both accretion disks and gravitational lensing are crucial observational evidence that strengthens the existence of black holes, allowing astronomers to study these fascinating objects without directly observing them. These indirect observations have been instrumental in confirming the predictions of general relativity and advancing our understanding of the extreme environments near black holes. Direct observations, LIGO-Virgo gravitational wave detection, Event Horizon Telescope imaging. Direct observations of black holes have become possible in the 21st century through revolutionary advances in technology and methodology, particularly with gravitational wave detection and radio astronomy imaging. LIGO-Virgo gravitational wave detection. The Laser Interferometer Gravitational Wave Observatory LIGO and the Virgo Interferometer have opened a new window into the cosmos through the detection of gravitational waves, ripples in spacetime caused by massive accelerating objects like black holes merging. These waves were first predicted by Einstein's general theory of relativity in 1916, but were not directly detected until 2015. LIGO detected the waves produced by two merging black holes, confirming the existence of binary black hole systems and providing a new method to observe the universe. Gravitational wave astronomy allows scientists to measure the masses and spins of black holes and the rate of expansion of the universe, and to test the limits of general relativity. Event Horizon Telescope Imaging. The Event Horizon Telescope 8 is a global network of synchronized radio observatories that work together to observe radio sources associated with black holes. In April 2019, the 8 captured the first ever image of a black hole, or more precisely, the shadow of the supermassive black hole in the galaxy M87's event horizon, which is surrounded by an accretion disk of glowing gas. The 8's observations were consistent with predictions from Einstein's theory of relativity, providing further confirmation of the theory's validity. The 8 continues to refine techniques to image black holes, aiming to produce even clearer pictures and to study the immediate environment of these enigmatic objects in greater detail. These direct observations do not show the black holes themselves, as they are invisible, but rather the effects that these extremely dense and massive objects have on their surroundings. Gravitational wave detections confirm the dynamic aspects of black holes in binary systems, while 8 imaging provides insight into the structure of matter in the immediate vicinity of the event horizon. Both methods are essential for understanding the nature of black holes and offer complementary information about their properties. Black holes and quantum mechanics. Information paradox. The black hole information paradox arises from a conflict between quantum mechanics and general relativity. According to quantum mechanics, information about a physical system is never lost, not even when objects fall into a black hole. However, general relativity predicts that once an object has fallen into a black hole, it is lost to the outside universe except for 3 parameters: mass, charge, and angular momentum as dictated by the no-hair theorem. When a black hole eventually evaporates through Hawking radiation, the information about the initial state of all particles that entered it seems to be lost. This contradicts the principles of quantum mechanics. Stephen Hawking initially proposed that the information about the ingoing particles is irretrievably lost from our universe. But the conservation of information is a fundamental part of quantum theory, and losing information would mean that the quantum description of the universe would be incomplete. It would not be possible to predict the future from the past, i.e., a loss of determinism. There have been various proposed solutions to this paradox. One suggests that the information is not lost, but rather encoded in the Hawking radiation emitted by the black hole, though the exact mechanism of how this could occur is not well understood. Another idea is the holographic principle, which suggests that all the information contained within a volume of space can be represented as a hologram, a description on the boundary of that space, such as the event horizon of a black hole. More speculative ideas include the notion that the information is stored in a Planck scale remnant after the black hole has evaporated, or that it exits into another universe if our universe is part of a multiverse. The firewall hypothesis proposes that an incoming particle would be incinerated by a high-energy firewall at the event horizon, resolving the paradox by suggesting that the information is released early on. But this contradicts the equivalence principle of general relativity, which posits that crossing the event horizon should be an uneventful experience. The information paradox remains one of the most important unsolved problems in theoretical physics, as its resolution is expected to require a quantum theory of gravity that successfully integrates the principles of quantum mechanics with those of general relativity. Quantum gravity and the search for a unified theory. Quantum gravity represents the field of theoretical physics that seeks to describe the gravitational force within the framework of quantum mechanics, and it is a critical component in the quest for a unified theory of everything. The aim is to reconcile the principles of general relativity, which describes gravity at the macroscopic scale, with quantum mechanics, which governs the subatomic world. In general relativity, gravity is not a force, but a consequence of the curvature of spacetime caused by mass and energy. However, quantum mechanics describes the other three fundamental forces using quantum field theories, where forces are mediated by particles: the strong nuclear force by gluons, the weak nuclear force by W and Z bosons, and electromagnetism by photons. The challenge is that attempts to apply the same quantum framework to gravity have led to non-renormalizable infinities, meaning that the equations do not make physical sense at very small scales. Several approaches to quantum gravity are being pursued. String theory. This posits that the fundamental constituents of reality are one-dimensional strings rather than point-like particles, and these strings vibrate at different frequencies to manifest as different particles. The theory naturally incorporates gravity by including a particle called the graviton, which mediates gravitational forces. String theory requires extra dimensions of space and is a leading candidate for a theory of everything. Loop quantum gravity LQG. LQG is a theory that attempts to describe the quantum properties of the universe without the need for extra dimensions. It suggests that spacetime itself has a discrete structure at the smallest scales, composed of tiny loops woven into a fabric. This theory directly quantizes spacetime and does not assume a background space in which events take place. Quantum field theory in curved spacetime. This approach accepts the curved spacetime of general relativity, but applies the principles of quantum field theory to this curved background. While it has had success in describing phenomena such as Hawking radiation, it does not offer a full quantum theory of gravity because it still treats the geometry of spacetime as a classical background, not subject to quantum fluctuations. M-theory. M-theory is an extension of string theory that unifies the different versions of string theory into a single framework. It posits an 11-dimensional universe where membranes branes of various dimensions are fundamental, and our observable universe might be a 3-dimensional brane within this higher dimensional space. Canonical quantum gravity. This approach attempts to apply the principles of quantum mechanics to the entire universe's geometry. It's one of the oldest approaches, but has been largely overshadowed by string theory and loop quantum gravity. The correct theory of quantum gravity is expected to solve many of the current problems in theoretical physics, including the nature of black holes, the singularity at the beginning of the universe, and the unification of forces. While significant progress has been made, particularly in understanding the possible implications of such a theory, a fully developed, experimentally confirmed theory of quantum gravity remains one of the most important goals in physics. Recent developments in theoretical physics continue to push the boundaries of our understanding of the universe. While a complete and unified theory of quantum gravity remains elusive, there have been numerous significant advances across various areas of theoretical physics. Here are a few highlights. Gravitational waves. The direct detection of gravitational waves by LIGO and Virgo has opened up a new field of astronomy, allowing us to observe the universe in a way that is not possible with electromagnetic radiation. This has profound implications for our understanding of black holes, neutron stars, and even the potential to probe the very early universe. Black hole imaging. The Event Horizon Telescope's groundbreaking image of the supermassive black hole in M87 has provided new insights into the nature of black holes and confirmed general relativity's predictions under extreme gravitational conditions. This achievement has also spurred new theoretical work on black hole physics. The muon G2 experiment. Recent experiments with muons particles similar to electrons, but heavier, have suggested that their magnetic moments differ from what is predicted by the standard model of particle physics. This could indicate the existence of undiscovered particles or forces, and has the potential to bring about a major shift in particle physics. Dark matter and dark energy. While these components are thought to make up most of the universe's mass energy content, they remain mysterious. Experiments such as the Large Hadron Collider LHC and observations from telescopes like Hubble and the upcoming James Webb Space Telescope continue to search for clues about the nature of dark matter and dark energy. Neutrino physics, the discovery that neutrinos have mass, which requires physics beyond the standard model, has led to intense theoretical and experimental activity. The nature of the neutrino mass hierarchy and the possibility of neutrinoless double beta decay are areas of particular interest. Quantum computing and information. Advances in understanding quantum entanglement and computing have profound implications for information theory, cryptography, and our understanding of quantum mechanics itself. These developments could revolutionize how information is processed and secured. Amplituhedron, a geometric object that has the potential to simplify the calculations of particle interactions by encoding particle interactions in a geometric volume without the traditional space-time framework. String theory and holography, the holographic principle, which suggests that a lower dimensional boundary can encode the information content of a higher dimensional volume, continues to be a significant area of research. It has applications in understanding black holes and has led to the development of the anti-de Sitter space-conformal field theory adst correspondence, a theoretical framework that provides insights into quantum gravity and strongly coupled quantum field theories. These developments reflect the dynamic and continually evolving nature of theoretical physics, which steadily advances our understanding of the fundamental constituents and forces of nature. Impact on the universe. Role in galaxy formation and evolution. Supermassive black holes appear to play a fundamental role in the formation and evolution of galaxies, exerting influence far beyond their immediate surroundings. Regulation of star formation. The energetic processes associated with accretion onto supermassive black holes can drive powerful outflows of material into the host galaxy. These outflows can heat up the surrounding interstellar medium and expel it from the galaxy's central regions, preventing the collapse of gas into new stars. This self-regulating mechanism is known as feedback and is considered vital in shaping the size and stellar content of galaxies. Galactic dynamics. Supermassive black holes have significant gravitational influence within their sphere of influence, which can extend over regions much larger than the black hole's event horizon. They can affect the orbits of stars and gas clouds in their vicinity, contributing to the dynamics of the galactic core. Bulge black hole mass correlation. Observations have revealed a correlation between the mass of the supermassive black hole at the center of a galaxy and the mass of the galaxy's bulge. This suggests a co-evolution of galaxies in their central black holes, where the growth of one is linked to the growth of the other. Quasar and AN activity. During the peak of galactic evolution, when galaxies were actively merging, the accretion of material onto supermassive black holes led to the appearance of quasars and active galactic nuclei and some of the most luminous objects in the universe. These phases of extreme brightness can influence the intergalactic environment, contributing to the reionization of the universe and affecting the formation of galaxies in the early universe. Seeding of galaxies. The formation of supermassive black holes is thought to precede the formation of the stellar component of galaxies. As such, they may act as seeds around which galaxies form. The gravitational well created by a supermassive black hole could help to attract and retain gas and dust, which can then form stars and contribute to the overall mass of the galaxy. Galactic collisions and mergers. When galaxies collide and merge, their central black holes can also merge. These events are not only powerful sources of gravitational waves, but can also result in the reshaping of the merged galaxy, potentially triggering new episodes of star formation or AN activity due to the influx of gas into the galactic center. The intricate interplay between supermassive black holes and their host galaxies is a key subject in astrophysics, with implications for our understanding of the life cycle of galaxies, the distribution of matter in the universe, and the processes that drive cosmic evolution. Black holes as potential energy sources. The concept of using black holes as potential energy sources is a speculative idea grounded in the physics of black holes and their ability to convert gravitational energy into other forms of energy. Here are a few theoretical ways in which black holes could serve as energy sources. Hawking radiation. Hawking radiation is the theoretical emission of particles from just outside the event horizon of black holes due to quantum effects. For stellar black holes, this radiation is extremely weak, but for hypothetical microscopic black holes, it could be substantial. If such small black holes were to exist or could be created, they might emit significant amounts of radiation that could be harnessed as power before they evaporate completely. Penrose process. The Penrose process is a mechanism where energy can be extracted from a rotating black hole. This process involves dropping an object into the black hole's ergosphere, a region outside the event horizon where space and time are dragged around by the black hole's rotation. The object is split into two, with one part falling into the black hole and the other escaping to infinity. If the escaping piece has more energy than the original object, energy has effectively been extracted from the black hole's rotation. Accretion disk energy. The material in the accretion disk around a black hole is heated to extremely high temperatures as it spirals inward, emitting large amounts of electromagnetic radiation, particularly X-rays. This energy comes from the gravitational energy of the infouling material and, in principle, could be collected and used. Blandford-Zeenagic process. This is a method for extracting electromagnetic power from a rotating black hole. It involves the creation of magnetic fields by the ionized matter in the accretion disk, which then interact with the black hole's spin. This interaction can generate jets of plasma that move near the speed of light, carrying away energy from the rotation of the black hole. While these methods describe processes where energy is released due to the presence of a black hole, harnessing this energy on a practical level poses immense technological challenges and is currently in the realm of science fiction. For instance, the immense gravitational forces near a black hole would make it hazardous to approach, and the distances to the nearest black holes are prohibitively vast with current technology. Moreover, the energy emitted by natural processes near black holes is not focused and would be difficult to capture and convert into usable power. Theoretical models like the Blandford-Zeenagic process involve conditions and scales that are beyond our ability to manipulate or replicate. Therefore, while black holes can theoretically be considered as powerful energy sources, practically utilizing them is beyond our current and foreseeable capabilities. Hypothetical scenarios: white holes, wormholes. White holes and wormholes are hypothetical entities that emerge from the equations of general relativity, though they have not been observed in nature. White holes. White holes are theorized as the theoretical time reversal of black holes. While a black hole acts as a one-way membrane through which matter can only enter, a white hole is posited to be a region of space-time that cannot be entered from the outside, only exited. Essentially, it's a black hole running backwards in time. Matter and light could emerge from a white hole, but nothing could fall into it. The concept of a white hole is mathematically possible, but white holes are considered highly speculative because they violate the second law of thermodynamics, and there is no known process by which they could form. Wormholes. Wormholes, also known as Einstein-Rosen bridges, are theoretical passages through space-time that could create shortcuts for long journeys across the universe. Wormholes are solutions to the equations of general relativity that contain two mouths connected by a throat. If traversable, they could allow travel from one part of the universe to another part of that same universe very quickly, or could even allow travel from one universe to another. Wormholes require exotic matter with negative energy density to keep the throat from collapsing. This exotic matter is hypothetical, and its existence is not supported by current experimental evidence. Additionally, any wormhole that could allow human traversal would need to be stable enough for matter to pass through without being destroyed by tidal forces, which seems highly unlikely given our current understanding. Both white holes and wormholes are of great interest to physicists because of their intriguing properties and the possibilities they suggest for energy, travel, and the fundamental nature of the universe. However, they remain in the domain of speculative theoretical physics, with no experimental or observational evidence to suggest that they exist in reality. They are useful tools for exploring the implications of our physical theories and for challenging our understanding of the nature of spacetime. Cultural and philosophical implications. Black holes in science fiction and popular culture. Black holes have captured the public imagination and have become a staple of science fiction and popular culture, often serving as a plot device that allows for exploration of deep space, time travel, and alternate dimensions. In science fiction literature, black holes are often depicted as gateways to other parts of the universe or as central elements in space exploration narratives. They can be the basis for complex stories involving advanced civilizations harnessing the power of black holes or the catastrophic threat that a black hole could pose to planets or entire star systems. In film and television, black holes are frequently used as dramatic settings or catalysts for plot developments. Movies like Interstellar explore the concept of time dilation near a black hole's event horizon, while others, like Event Horizon or The Black Hole, depict them as portals to other dimensions or universes. Video games also use black holes to create narrative intrigue or as gameplay mechanics. They might serve as shortcuts between different areas of space, dangerous obstacles to be avoided, or even as energy sources for the game's characters or civilizations. In popular science, black holes are often used to explain the fascinating and mind-bending concepts of modern astrophysics, from the warping of space-time to the limits of our understanding of physics. Notable physicists like Stephen Hawking have written extensively about black holes, bringing complex theoretical concepts to the public in an accessible way. In educational contexts, black holes are used to spark interest in astronomy and physics, illustrating the extreme environments in the universe and providing a tangible example of the effects of gravity. However, the portrayal of black holes in popular culture often diverges from scientific accuracy, sometimes significantly. They are frequently anthropomorphized or attributed qualities they do not possess, such as an insatiable hunger or malicious intent. Despite these inaccuracies, the use of black holes in popular culture has been important in raising awareness and interest in space and the cosmos, inspiring both awe and a desire to understand the universe more deeply. Recent discoveries and research. Cutting-edge research in black hole physics. Cutting-edge research in black hole physics is pushing the boundaries of what we understand about the universe. Here are some areas where significant advances are being made. Gravitational wave astrophysics. Following the first detection of gravitational waves from merging black holes by LIGO and Virgo, researchers are now using these observatories to regularly detect such events. This has opened a new era of astrophysics, where scientists can study black holes and neutron stars by analyzing the gravitational waves they emit when they collide or merge. Event Horizon Telescope 8 and imaging of black holes. After the first image of a black hole's event horizon was captured, the 8 collaboration is working on new observations. They aim to produce more images of black holes and to study their event horizons in even greater detail. This could provide new insights into how black holes grow and how they affect their surrounding environments. Black hole information paradox and quantum information. Theoretical physicists are delving into the black hole information paradox and the interplay between quantum mechanics and general relativity. There is ongoing research to understand how information is preserved in the universe, particularly looking at the role of the event horizon and the possible connections with quantum entanglement, known as R equals Epper conjecture. Accretion disk physics. Scientists are studying the physics of accretion disks, which are structures formed by material falling into black holes. By examining the light emitted from these disks, researchers can test models of how matter behaves in the extreme gravitational fields near black holes. Tests of general relativity. Black holes provide natural laboratories for testing the predictions of general relativity under conditions of extreme gravity. Observations of stars orbiting around the supermassive black hole at the center of the Milky Way, as well as the study of gravitational lensing, offer tests for Einstein's theory. Simulations of black hole mergers. Advanced simulations are helping astrophysicists to predict the outcomes of black hole mergers and the resulting gravitational waves. This is crucial for interpreting the signals detected by LIGO, Virgo, and future observatories like LISA Laser Interferometer Space Antenna. Hawking radiation and black hole thermodynamics. Experimental efforts are underway to detect Hawking radiation from black holes. While direct observation is currently beyond our reach, analog black hole systems in laboratories using fluids or Bose-Einstein condensates are being used to explore the principles of black hole thermodynamics, primordial black holes, and dark matter. Researchers are exploring the possibility that primordial black holes, which could have formed in the early universe, might make up some or all of the dark matter. There are multiple observational campaigns looking for evidence of these black holes through microlensing and other effects. This ongoing research is not only enhancing our understanding of black holes themselves, but also providing deeper insights into the fundamental laws that govern the universe, from the smallest scales of quantum mechanics to the cosmic scale structure of spacetime. Conclusion. Recap of main points. In recapitulating the main points concerning black holes, definition and nature. Black holes are regions in space where gravity is so strong that nothing, not even light, can escape. They are predicted by Einstein's general theory of relativity and have been confirmed by numerous observations. Formation. Black holes can form from the remnants of massive stars following a supernova explosion, or through other processes for supermassive and intermediate mass black holes. Types. There are three main types of black holes: stellar, which are up to 20 times more massive than the Sun; supermassive, which are millions to billions of times more massive and usually found at the centers of galaxies; and intermediate, which bridge the gap between stellar and supermassive black holes. Properties. Key properties of black holes include the event horizon, the singularity, mass, charge, and spin. The no-hair theorem postulates that black holes can be fully described by these three observable properties. Observation. Black holes can be observed indirectly through effects, such as accretion disks and gravitational lensing, and directly through means such as the detection of gravitational waves and the imaging of the event horizon. Quantum effects. Theories such as Hawking radiation predict that black holes emit radiation due to quantum effects, leading to the black hole information paradox, which challenges our understanding of physics. Role in the universe. Black holes influence the formation and evolution of galaxies, potentially regulate star formation, and contribute to the dynamics within galaxies. Cultural impact. Black holes have become a part of popular culture and serve as significant elements in science fiction and educational contexts. Current research. Cutting-edge research in black hole physics is advancing our understanding of gravitational wave astrophysics, the nature of quantum gravity, and the potential connection between black holes and dark matter. These points only scratch the surface of the complex and rich field of black hole physics, which continues to be an area of active and fruitful research in modern astrophysics. Reflection on the importance of studying black holes. Studying black holes holds profound importance for advancing our knowledge of fundamental physics, as they offer a unique testing ground for theories of gravity and quantum mechanics. They serve as astrophysical laboratories where we can observe the behavior of matter under extreme conditions, providing insight into the high-energy physics that is impossible to replicate on Earth. Black holes are also thought to play a crucial role in the evolution of galaxies and the large-scale structure of the cosmos, potentially holding the key to understanding dark matter and the fate of the universe. The technological innovations driven by black hole research often have wider applications, pushing the boundaries of current technology. Culturally and philosophically, black holes have captivated the human imagination, influencing art and literature, and serving as a symbol of the enigmatic universe, inspiring curiosity and a drive for discovery across generations. The allure of black holes lies not just in their mysterious nature, but also in their capacity to unify various fields of study, from theoretical physics to cosmology, and to spark the collective imagination in pursuit of understanding the cosmos. As we draw this exploration of black holes to a close, it's clear that these enigmatic features of our universe are more than just regions of intense gravity. They are canvases upon which the universe paints some of its most profound mysteries. They challenge our understanding of the fundamental fabric of reality, blur the lines between space and time, and continue to puzzle even the most brilliant minds. Our journey through the cosmos, with black holes guiding the way, has shown us the incredible power of human curiosity and ingenuity. From the theoretical equations on a chalkboard to the most sophisticated telescopes peering into the depths of space, we are unraveling the cosmic tapestry one thread at a time. So, as we sign off from this episode of The Sleepy Scholar, let us take a moment to appreciate the vastness of the universe and the small, yet significant, place we occupy within it. May the quest for knowledge keep our eyes ever upward, and may the secrets of the universe continue to unfold before us. Thank you for joining me on this voyage into the abyss. Until next time, keep wondering, keep pondering, and most importantly, keep exploring. Good night.